And also I want to thank you and Gabor for giving me the chance to give this talk and inviting me to do this. So without much ado, let me go to the topic here. So I'll first talk a little bit of, always do that. Talk a bit about structural properties of systems with delays. Most of us, of course, do know about that already. And then I will talk about some, this time, not so much engineering aspects, but rather physical aspects, an application in post-Newtonian gravitation. And then I actually conclude with a caution that naive approximation can be dangerous in these systems. So first, let's look at structures of systems with delay. This is very elementary here, but start with equation 1, which shows a fixed delay. Then it's been known for decades that if we take this Lyapunov functional here of this form with the integral, is sort of inspired by Lurie's method, then if we can investigate the derivative of v along the solutions of 1, we see that we get or can get this expression. So here, this we don't worry about because that's always negative definite. This is a purely symmetric term here. But here we see a quadratic form with this Riccati type combination, or quadratic form in P in between here, that leads us to a sufficient condition for stability. And that is, if there exists matrices P, Q, and then R, which is actually the negative of that are positive definite, such that this, I call that the Riccati equation, holds, then we have stability. Now, this was the first time that where this appeared was in 91 at the rather obscure conference in Warsaw in Poland. It was later published in 94, but this was at a time when CDC did not have any sessions on delay systems. This was all still absorbed by linear systems. Then in 94, I did an extension on time-varying systems. And so here is this time-varying extension. There is a key issue, and that's that the delay derivative should be less than 1. And the idea is, again, use similarly Lyapunov functional, but you put the P and the Q now as time-varying matrices. And then again, along solutions of the functional differential equation 2, you can show that V dots is of this form. So again, we have this symmetric quadratic term with a negative sign, but it also has 1 minus tau dot. So that's where the key issue comes in. If tau dot is less than 1, this term is negative definite. We don't need to worry about it. And we have then an equivalent, again, a quadratic condition or a Riccati condition for stability. Now, the key is that since then, there has been an explosion, literally an explosion on work on delay systems. The CDC and ACC did not have just one, but actually multiple sessions on delay systems ever since. And a lot of people also worked on the stability criteria when tau dot is larger than 1, thinking that the condition that I had tau dot less than 1 is just a technical condition to make this proof work. But that's actually not the case. Tau dot less than 1 is intimately related to the notion of causal dynamics. And the confusion may stem from the imprecision that one may have in the notion of state space and information structure. Let me go to a very simple example and just non-delay example. If we look at the two systems side by side here, x dot is ax and x dot is ux. Well, to a mathematician, there is no difference. But in a control systems person will say, well, here u is an input, so this is a bilinear system. And this, well, I see a times x, so that's a linear system, but it's time variant. But what is really the major difference between the two? When we look at this and interpret that as a time variant linear system, it is assumed that for each time t, we know the entire history, that is the past and the future of a. So the entire function is known. While if we do control, we only know, well, we may have a record of the past controls that we used, but we can never know what we are going to use in the future. So this is basically what is stated here. So to make this thing precise, I suggest that we introduce something like as done in stochastics, introduce sigma algebras and infiltrations to make precise what information about the system is known at what time. And for a delay system, that means that do we know the delay, the entire delay function, if it's time variant at any time, or in the case for a state-dependent delay, which I will talk about, this may be dubious because we may not know what the state will do and therefore don't know what the delay will be. Okay, but first let's look further and time varying delay system when tau dot is less than 1. If that condition is satisfied, then the state space is still equivalent to this simple functional function state here. And when t minus tau t is decreasing, that means when tau dot is larger than 1, no homeomorphism to this form can exist. And so we have shown that the problem is no longer well posed in the sense of Hadamard in this case. So the key is to maintain tau dot less than 1 as a condition. Now, if you really insist on tau dot larger than 1, you can fix it, but then you have to change the structure of your system because one thing we introduced was the so-called lossless causalization. And that means if we know that's the maximum time delay, then you actually propagate the system always over that maximum time delay. And the internal dynamics can switch faster than 1 then, but you're always propagating this. If that's not the case, think of the delay as being a shift register in discrete time, and you vary the length of the shift register. Well, once you have a short shift register and it expands very fast to a longer one, what are you going to put in that shift register? You don't have the data available. So I call that forgetful causalization. We make it causal again, but we may be stuffing that shift register with zeros. And so these topics that relate to the analysis of fast varying delays was presented at the CDC in 2011 by Wim and myself, and also at the IMA Journal of Mathematical Control and Information. Now, for the construction of the state space, so I assume that at any time t, the entire delay function is known. So that's part of the structure of the system. And then we just have the original form of the system right here. And we try to find a transformation from t to lambda, and then set x of lambda of t as x bar as lambda. And so if we can find the transformation that maps x into x bar lambda and xt minus tau in x bar lambda minus 1, then we have succeeded in building that homeomorphism. And that turns out we have to solve for this transformation. T is t of lambda. It satisfies this relation with respect to the original delay function tau. So in general, this is a horrendous thing to solve. So it's only conceptually that we can use this. However, if you take a simple problem, tau of t is 1 plus gamma t. So here I have up to time 0. The delay was equal to tau. Oh, by the way, I'm So the time t, the horizontal axis is the time axis. And if the delay is 1, I take, so from 0 to -1 would be the delay. I moved it over perpendicular to the time axis. And so the vertical axis is actually the stuff that was in the delay. So it's a somewhat nicer interpretation of a delay equation. So at each time t, here is the state, is the function. The value of the function is encoded by the caller. And now you see, indeed, if gamma is less than 1, these color bands nicely fill this. But imagine now that gamma is larger than 1, and so you have something like here, then you see that you're missing information that you cannot put in there. So this system would not be well defined. Okay. So after the for that example, and here in the example, this is the time transformation. It's this logarithmic form here. Then we see that indeed we have reduced the system to in the lambda as time variable to one with fixed delay, and can be solved as before. Okay, now let's look at implicit state-dependent delay. That is inspired by a seminal work of Hans Otto Walter, who was then in Munich. Think of maybe a submarine that's going to land on the ocean floor. And so at t minus tau, it sends a sonar signal that travels and bounces back from the ocean floor and gets received by the submarine at time t. But of course, at time t, the submarine is at another position. So what we need for a model is first the dynamical equations for this. So typically that would be simple first or second order model. But then we have the time travel for the wave. So if the wave or the sonar signal moves at velocity c times tau would be the sum of yt minus tau plus yt. Okay, and so we have this implicit relation here. And so the problem is, well, if we think of encoding a timestamp on the sonar signal, then what's observed is actually the delay time. And so from the delay time, measured delay time and the known dynamics, we want to estimate the state of that system. Okay, a simpler model is actually if we only have a beacon here and so with the receiver, and we want to detect the position of the mobile unit. So this would be the one-way problem. In this case, yt minus tau is equal to c tau. Now let's check the causality constraint. If I simply take the derivative of that, and remember that when you take the derivative, you also have to, so it's y prime of t, but also times 1 minus t dot, because you need to do the chain rule here. So then the tau dot appears on both sides. You put it on one side, we get this relation. Okay, now you see that if v is less than c for all time, so this is less than 1, this is less than 1, so tau dot is indeed going to be less than 1, so the criterion is satisfied. In the two-way problem, we do the same thing. You take the derivative of this relation with respect to t, single out the tau dots on one side, we get this relation. Again, if the velocity or the speed of the submarine is less than the speed of sound, then this quantity is going to be less than 1, and we're all set. Okay, so how can we now invert this or solve such an implicit equation? Well, as I said, we assume that tau is available. So here I take c times tau. And from this value of c times tau, we can just do simple geometric construction. So we come down with slope c here. from the observed point. That gives us t minus tau. And then the x at t minus tau is precisely equal to c tau. So this is simple deconstruction. So you get the value, you come down here, and then copy the value that we had here over here. So from the blue line of the observed time delay, we get the actual position x here. It helps, of course, to have a pinning condition. That means for some time t0, I assume that x of t is fixed to x0, and x0 is known for this initial time. And then also the time delay at this initial position is known. Otherwise, you have some unknowns in the problem. So this could be just the mooring condition, and then when the device starts moving, then you collect data. Okay, so let's look now at what we can. So in general, I take now a model that g of tau is some function of y of t and y of t minus tau. So I generalize this implicit delay condition a bit. Okay. Now, if I assume that f is k1 times differentiable, g is k2 times differentiable, and y is k3 times differentiable, and k is the minimum of all these three integers, but is large, and that minimum is larger than 1, then it turns out that this r function here, which is basically the difference, so we want the r function to be 0, but this r function is, on the right-hand side at least, is then k times differentiable. And if now the Jacobian of the r d tau does not vanish at that point, then we know by the implicit function theorem that there exists a transformation so that t of little t is going to be tau in this neighborhood. Now we can actually do better if we know that f, g, and y are not just differentiable but are actual analytic functions. Then I have shown that if y is analytic, or sorry, y is analytic if and only if tau is analytic. So here we get a lot more information besides just existence of the inverse. Now, as a corollary, if y is generated by a finite dimensional linear time invariant ordinary differential equation and u is analytic, then we know that y is analytic. So by the theorem I just cited, that means that tau is analytic. And now I can use the Lagrange-Berman inversion, which is actually a theorem that's powerful but little known and usually is not taught in the calculus courses. But given f mapping from R to R, that's analytic, and if f0 is 0 and the derivative at 0 is not 0, then ft of x can be inverted as series expansion in x. And Good in 1960 gave a multivariate extension of this. Okay, so the problem is that the Lagrange-Berman inversion is not directly applicable to this system, but we can actually trick it into getting there. So here is theorem 2. If the derivative of g plus f2 means that's the derivative of the f function with respect to the second argument. So if f2yy plus g prime is non-zero at t, then the inversion at t is explicitly given by this expression here. And that's directly by using the Lagrange-Berman inversion on this function f of tau right here. And so as an example for the passive localization of the mobile unit and the landing problem at the ocean, we have, for instance, that tau at time t given that we had this spinning condition, tau t0 is x0 over c0, is given by this series expansion. Now, the x dot and x double dot bracket x0 means that this is x dot at time t such that x0 t such that xt is equal to x0. Okay. So yeah, that's again the same Lagrange-Berman inversion now for the two-way docking problem. Here is an example. So I assume here that the observed time delay is this parabola. And I assume that you have the pinning condition that I know that at time zero, the position was exactly at zero, and then with also zero time delay. And then we, from this delay function, I try to infer the position. Well, you see that the position is given by this lopsided arch here. But you see, this is the first order expansion, second order, third order, fourth order. So we see we get closer and closer to the real deal, but there is weird behavior and when t is equal to 1. And that is, of course, that because at that point, there no longer is, the function is no longer analytic because there is a pole at that point. And so the approximation goes haywire there. So another thing one can do is look at the perturbation expansion. Okay, so again, here is our implicit relation. Write xt as c tau minus xt minus tau, and then this xt minus tau is again expressed as ct plus or minus x and so on. So we get an infinite series of delays here. This can be encoded like this. And then the series expansion here is x of t is this alternating sum of these taus. Now, since tau t is less than t, these guys here are all less than 1. So the sequence tk is monotone and converges to 0. And therefore, the alternating series or the perturbation approach is known to converge. Okay, so applications of this implicit state-dependent delay is, as I mentioned, sonar-based position in the ocean. This implies also stream field estimation in the ocean, which uses the first. If we don't want to work in the ocean, but want to work with electromagnetic waves, well, we need to go to a deep space network before we have reasonable delays. So also deep space network-based navigation has same type of problem. And another example is the mass concentration identification on the moon in the GRAIL project. That's when two satellites were moving in the same orbit past each other. And if there's a mass concentration in between, that means that the first satellite will be somewhat slowed down and the second one sped up. So the distance between the two satellites gets smaller. And when they move away from the mass concentration, it gets larger again. So this was a way of identifying masses on the moon. And of course, what I will talk about now is the second part of my talk, post-Newtonian gravitation. So let's do a little bit of physics here. Let's recall that everyone knows Newton's law. Force of gravitation is inversely proportional to r squared. And of course, that has been improved by Einstein in this complicated looking thing here. G and T are tensors. G is the Einstein tensor. This basically models the curvature of space-time. It's the Ricci curvature and scalar curvature together in one tensor. And T is the stress energy momentum tensor. And this quantity in brackets here is called Einstein's gravitational constant. So Einstein connects matter and energy, that's the right-hand side, with the geometry of space-time. Now, the mu and nu here are indices of the space-time coordinates, so it's four-dimensional. So each of these tensors has 16 components. Therefore, this is a set of 16 coupled nonlinear partial differential equations. Now, it's somewhat redundant because of the symmetry. And so if we take away the symmetry, we only have to deal with 10 nonlinear coupled PDEs, which is still horrendous, and few exact solutions are known. One exact solution is the Schwarzschild solution observed or obtained by Schwarzschild in 16. But even for a simple case of two massive bodies, there is no explicitly known solution for this problem. Only computer simulations can get there. And such a simple problem is actually a theoretical model for a binary star system. So because of this complexity, it would be of interest to find a simplification. And so I'm getting a simplification here with the following assumptions. We continue with the idea that the gravitational potential of mass density field. And so that means that I assume that at time t prime, I have a mass distribution. So may be different at any point r prime. But to express this requires a notion of simultaneity, which is directly in contrast with or inconsistent with special relativity. So to allow this, I need to assume small velocities. Okay, so that's one. Then also gravity cannot act instantaneously. That's my second argument. And I assume that the finite propagation speed for gravity is the light speed. It cannot be faster, or you could signal in principle using gravity. And that also will contradict the special theory of relativity. So I postulate that the density field that I assume that requires notion of simultaneity still generates a potential, and that potential is the superposition of all the infinitesimal contributions. And also the contributions from r prime must have traveled a straight line distance from r to r prime, and that takes a propagation time equal to this. So this is the delay due to the propagation. All right, so only the past value of the mass distribution at point r prime will contribute to the field at rt. Now, also what I'm assuming here, you see, I assume straight line distance. General relativity implies warping of space and time, so geodesics are no longer straight lines in general. So to justify this, I need to assume weak fields. So two assumptions I make: small velocity and weak fields. Okay, so this is what we have here. And then, all right, so let's write the contribution to the potential at point r at time t, as all these contributions, dv is the volume element at r prime, and so here we see the delay. The Newtonian case, of course, would just be no delay here. Okay. And this delay, this equation is then coupled also to this implicit delay function. All right. Now, to simplify this, I will assume that the mass distribution is only due to a unit point mass in motion. So the distribution of the density is given by this Dirac density for a point mass moving at a precise trajectory, rp, at time t. And then the gravitational potential, of course, you put this delta Dirac potential in there. And we note that, first of all, that when r is equal to r prime, this integral is going to be singular, but we can do away with that because this is going to be isotropic. So if we take the principal value, this would be zero in a small neighborhood. So we don't worry too much about that singularity. Okay. Now I take a derivation analogous to the Leonard-Wiechert potentials for electromagnetism. And in an earlier approach, in 15, I actually did that by directly evaluating this integral. But the Leonard-Wiechert approach is somewhat simpler. But you have to do some activation energy first. So you actually make this more complicated by taking a four-dimensional integral, including space and time, change integration, and then reduce that four-dimensional to a one-dimensional time integral. So that's what I will do here. So theorem one is that the potential is given explicitly by this form. And so here is what's in blue. So if you look here at the arguments of the delta function, I had here RP at the back, B stands for backward time. So that's the delay time. Okay, so now I take here any time t prime, but then multiply by the Dirac function of time t prime, the one that peaks at t prime equal to TBR. So that's how I introduce now the time integral. I make that a four-dimensional integral. Now change the order of integration, or first integrate out the spatial part, and that gives us the potential simply as this time integral, where now we have Rp at time t prime. That's the trajectory at time t prime. Okay, I do now further transformation. So what this says is that I look at t prime 0 is actually t minus tau. So t prime 0 is the backward time. I should have called it t sub b, but I noticed too late to change the slide. So in terms of the backward time, and this takes now t prime is the time since the backward time. And I also use the fact that the delta of t prime times a constant is equal to delta t prime divided by the absolute value of this constant. So this reduces this delta function. Notice that t prime appears here and here as well. So I reduce that to delta t prime, and then we have the derivative of this, which involves the gradient of tau with respect to r prime times the speed at the point mass at the backward time. So we substitute that in the equation for the scalar potential and compute the gradient. And that's when I derive this formula. So this formula is actually somewhat nicer than this one, because I pull out of the r minus rp that's here in both terms. I pull it out over here. Okay. And then once we have the potential, the gravitational field is the gradient of the potential. So now I need, there will be two terms here. Oops. So if I compute the gradient with respect to r, first I have this term, this factor right here, and I have this factor right here. So it gives rise to the first term and the second term. Okay. So how do we get that? Well, need to do some well-known relations. So the gradient of the magnitude of a vector is given like this. Similarly, we get this here. Now, notice that this term is always less than 1, because v is always less than the speed of light. So this must be less than 1. So I can do away with the absolute value sign and just take the gradient of this, which is somewhat simplified. Then again, we take the gradient of a unit vector that's given by this times a projection operator, and this projection operator is onto the plane perpendicular to the vector r minus r naught. And so ultimately we get then this expression, the gravitational field in this post-Newtonian approximation is given like this. So it's a horrendous expression, but notice that in this last term here, because of this projection operator, if the velocity at the delayed time is parallel to r minus rp, so that's the line of sight from the observer r to the past position of the particle, then that term is 0. So we only have, under this condition, only have the first condition, which simplifies to a one-dimensional problem. So forced component due to unit mass test particle moving on a straight line through the point R is given like this. And we see two deviations from Newton's law. First of all, the squared distance is now the delayed position of the gravitating particle appears there. And then there is also an aberration that's based or due to the velocity of the position. And Newton's equation, Newton's force is independent of the velocity. So an analogy to electromagnetism, I call this a gravito-magnetic effect. And we should be careful because you might have thought that the generalization of Newton's law would simply be replacing x minus x prime by the delayed version, but that's not true because it misses this gravito-magnetic term. And that's a good thing, because if you have a binary star system like this, and we know that the force is directed towards the past position, then you see that this is the gravitational force would point to this one. Centrifugal force points here, which means that there is a net force in the tangent to this circle, which means that your binary system would keep spiraling out of control, would get larger and larger radius, and nothing could be stable. So it's a good thing that we have this magnetic term to correct for that. Now we can derive an alternative form in terms of the predicted position. So if at the backward time, so that's t minus the delay, if I know the position and I know the velocity, and we simply take this linear approximation of, so velocity times tau is the predicted distance that the particle has or still has to travel to time t, then in terms of this, I can replace the force or the gradient of the potential into this form. So now we have, we have r minus rp hat. So that's, the force is now in the direction of the predicted position. And we have again this term here depending on the delayed position, and this is another correction term. So this formula is a lot simpler than the previous one, and it conveys the same information. So theorem 2 says the gravitational force exerted by a particle in motion is directed towards the predicted position based on uniform motion given the position and velocity at the past time. This is an equivalent expression of this. So this looks equivalent now to Newton's condition, but where Rp is the predicted position. And there are two correction factors. This is actually the inner product between these two unit vectors, from R2 are the predicted position and the past position. And of course, this is this cosine term. So 1 over the cosine squared is always greater than 1. This term is the ratio between the length of this and the length of this, and that can be either larger than or less than 1. So if we have a particle moving at the uniform velocity, notice also that RP hat is the correct position of that particle. Okay, so now let's look what that implies. Let's look at the force due to gravitational current. So what do I mean by that? Well, let's assume we have an infinite bar, massive bar, and extends from minus infinity to plus infinity. And this bar is at motion. Since it's infinitely long, you actually may not see the motion, but it just moves. Okay, it's so like a gravitational current. And I place the observer here at the distance d from the bar. And let's first look at a small element of the bar that moves with velocity v. And then simple high school geometry lets us solve this equation for the delay. And we find with the previous formula that for that elementary part of the bar, position x0 and with velocity v0, we get an x direction of the force given by this horrendous form. But if you integrate now over all x of 0, so that means we integrate now over the entire length of the bar, then we see that there is a force in the direction of the motion of the bar, parallel to the bar. And that force is approximately linear, proportional to the velocity of the bar. This is v over c. I say approximately linear because remember my theory is only valid for small values of v. If you look at the y component, we can also compute that for the elementary particle at position x0. And then if you integrate over x0, then you see that, yes, there is this quadratic looking form here for the force of the particle. And of course, that's the known force, the Newtonian force, because if you're at the position d away from that bar, then yes, you will feel gravitational effects of that bar, and that will be second order in the distance. Okay. But so the new thing that we see here is that there is also an additive term which is linearly for the parallel component. And of course, 0 when the force is 0. Now you may wonder, what is the significance of this infinitely long bar? Well, if you look at the large-scale structure of the universe, it actually consists of all such bars. Each of these lanes here contains multiple zillions of galaxies all moving in unison. So this is the motion of a big, massive bar moving in one direction. So it does have some relevance. Now, an application also is the notion of dynamic friction. So imagine for a moment that you have a galaxy and a star is moving perpendicular into that galaxy. So what happens? Well, a star moves here, or we can think of the star being stationary and the galaxy moving towards the star. Well, the galaxy contains all these parallel bars of masses. So what we see now is the star moves into this field of bars or bundle of bars. The component of the gravitation directed towards the bars is going to be singled out to be 0 because it's completely isotropic. But in the direction perpendicular to the galaxy, we see that the bars will affect this entraining motion that I just talked about. And so the effect is that the star will be somewhat slowed down when it enters the galaxy. And so this means that it's the galaxy will feel like it's syrupy material where you drop something in. So there will be first order form, something like this here. So x double dots is this friction coefficient v minus x dot. So at equilibrium, the star will actually end up with the motion v of the galaxy will be entrained completely by the galaxy, and there will be no further slowing down. So galactic medium acts as a viscous medium to the star, and at equilibrium, the star moves in unison with that medium. Now let's look at the binary star system. Here, for simplicity, I take two equal masses. So this is so they're moving in counterclockwise direction. This star feels the effects, the gravitational effect of the other star when it was at a past position right here. And so we can now look at the predicted position. Predicted position, remember, is the past position plus the past velocity just traced out linearly to here. So this will be the predicted position. So it's a little bit further than the actual position at time t. And so if we look at the equations, so here is again the balance between the gravitational force, the post-Newtonian gravitational force, with the centrifugal force. And then we have simply these geometric equations. So I have to do some high school geometry here, but nothing involved. And we end up with this relation. If we eliminate then d, delta, and theta, this is the relation. So r is the radius of the orbit, and v orbit is the orbital velocity. So Newton's prediction would be 16, but without a square root. And with the post-Newtonian, we have this relation here. But you see, if you put the square root on the left-hand side, then you get m over this square root. And this square root is just Einstein's beta factor. And so that means that we look now at m over this beta factor is the relativistic mass. It's always larger than the real mass. So the post-Newtonian orbital velocity exceeds the Newtonian velocity, but it's exactly the same formula if you replace the mass by the relativistic mass. I've checked this also for binary systems that have unequal masses, and then they, of course, rotate on different radii. It gets a little bit more complicated, but again, each of the masses can be replaced by their relativistic mass, which will be different because they move now at different orbital velocities. But what we find is that the exact same relation comes out as Newton's relation, but we have to replace the mass by relativistic mass. Now, interestingly, last November, there was a paper in the Astrophysical Journal, paper based on observations, and it showed the breakdown of Newton-Einstein standard gravity at low acceleration in internal dynamics of wide binary stars. So this is actually the experimental verification of what I've just explained. Now let's look at the last problem is fission. Take two masses that are consolidated at the origin, and then they at time zero, for some reason they split apart. One mass moves to the left, the other equal mass moves to the right with equal velocity, equal initial velocity, and they're just we look at the gravitational effect. So again, if we look at mass, the rightmost mass here, it will feel the gravity of the leftmost mass at an earlier time. So it will feel this gravitational force right here. Now, in this case, when you have equal masses, we have symmetry between L and R. And I assume that Newton's law of forces, mass times acceleration, still holds. Then we get, applying the formula that I have derived in terms of the predicted position, we get this. We get the relation of, sorry, this is the definition of the predicted position, but here is the relation of the propagation of gravitation, the implicit state-dependent delay. You combine the equations to this form, and we see we get this second order differential equation, delay differential equation with this relation. I solve it by perturbation expansion. So expand the position r and the delay tau into the series. Notice that I put already the epsilon, which is 1 over c, in front of tau1 because tau is very small. Okay, then the velocity perturbation factor expands like this. You can write the expansion now, the differential equations of the perturbation terms in terms of the delays right here, and then the delay in terms of the positions right here, positions and their derivatives. And then if from the two sets of equations, if you eliminate the delays, we get these coupled differential equations. So this is the zeroth order. That's Newton's equation, essentially. That's the first order correction term that depends on R0 obtained here, second order, and so on. And now we see that if we look at the escape velocity of, according to Newton's equation, so all we need to do here is set multiply by r naught dots on both sides, and you can find a constant of the motion. And then if you make r dot equal to 0, that means you have the apex, and the apex of the motion should occur at r when r0 is equal to infinity. So that's the escape condition. So here the green line is Newton's approximation. And that's for the initial condition, which is exactly the escape condition. If I look at the first and second order approximation, then we have these terms here. So we see already first and second order are very close. But if you integrate that far enough, both of these approximations go back to 0. So that tells us that the Newtonian escape velocity is not large enough. I can generalize this for the asymmetric case. So let's assume we have an initial event like a nova or supernova explosion that takes the star apart into two parts. So this gives the initial kinetic energy, nothing relativistic here because this is all at position 0. I keep the center of mass at 0 for simplicity. And these two equations tell me what the velocities for the left moving and right moving mass have to be. And similar to the previous now, but now I have loss of symmetry, so I need two sets of equations, one for r double dot in terms of L dot, and same for L double dot in terms of r dot. And there is a delay tau here, tau and tau bar, that satisfy these symmetric looking relations. However, note that tau is not equal to tau bar if we have unequal masses. And you can easily see that by subtracting these two. If you assume that they would be that they will be equal, then r plus L at time t would be equal to r plus L at time tau seconds earlier, which means that r plus L is going to be constant, and that, of course, cannot happen in this case. So if we now compute the perturbation terms, again, this would be the two terms, the zeroth order term, that's the Newtonian approximation. And then I only show here the first term. The second term is also computed, but somewhat more complicated. It's quadratic in the quadratic. It's actually a Riccati equation. But here we see that if R1 double dot depends on R1 minus L1, so we can actually take a combination of these. And if R naught minus L dot is changing very slowly, this is actually the equation of an oscillator. So if R naught minus L dot is very slow, then we see that the first order perturbation term is some very slow oscillation. Okay, that's, of course, provided R naught minus L dot is small. Okay, the escape velocity for the Newtonian case, in terms of the initial energy of the event, has this simple expression here. And I've taken here some parameters. Again, I express the I plot the function for the Newtonian escape velocity, which is just between this number and this number somewhere. I didn't pin it down exactly, but it's between these two. And we see that, yes, for small enough times, the Newtonian approximate, that's the position of the rightmost mass, the leftmost mass, they're pretty much the perturbation doesn't add much. But if you integrate for a long, long time, then you see that, yes, first and second order perturbation make it coalesce again. So we do not have escape. That's interesting. So again, the escape velocity is larger than what Newton would predict. Finally, let's look at the rectilinear motion of a particle with constant velocity, v naught. And we wonder, is there anything about its self-gravitation is there an effect from its own past position that may affect it? Well, if we look at the state-dependent delay equation, then we would have this relation. So c is the propagation time of the delay, but that has to match the speed of the particle. So this cannot be satisfied unless v naught is equal to c. But in that case, then we have the same contribution from all the past locations. And if I put that in the integral, we see that r minus the predicted position is always going to be here, no matter what delay time I look at. So this is always zero. So this integral will blow up in your face, except when m is zero. So here we have the interesting result that a particle moving at limit speed, that's the speed of light, has to have zero mass, or it is not possible otherwise. And I wonder if there is a converse. If a particle with zero mass always has to move at the speed of light. I cannot answer this because this is actually outside the bounds of my theory. Remember, my assumption was that V naught was small, and here I find that V naught has to be equal to C. So that's not correct.
Erik, I'm
Yes.
sorry for interrupting you. Could you a bit watch time? Because we are now past 5 o'clock.
Okay. Well, I'm going to skip this thing here. I'm just going to end my my conclusion here. So I have 3 results that I basically mentioned as the engineering part is the inversion of state-dependent delay. Actually, you can read that in my chapter in the book on the recent results on nonlinear time delay systems, the Springer-Verlag 2015. Then I talked a bit about the physics, and I singled out the post-Newtonian gravitation because I thought that was an interesting thing. I talked about fields of mass in a uniform motion. I talked about the gravitational current, dynamic friction, binary, binaries, escape velocity for splitting mass. What I have not yet looked at, but that I plan to do, is the notion of the galaxy rotation curve that was inconsistent with observations and Newtonian theory. And this was solved by invoking dark matter. If there is more matter in the universe, actually 6 times more matter in the galaxy than we can see, then it would explain the rotation of the stars at the edge of the universe. But now, since I have this modified theory, maybe this post-Newtonian can take some of the dark matter away. And this is the part that I actually had to delete, but you sometimes should look, when you solve problems, you should first do the physics, make sure that your assumptions and your model is sensible and makes sense, and then do the math rather than do the math first and come up with nonsensical equations. So thank you very much for your attention, and I apologize for running over time a bit.